So welcome to the second video for this week as we resume our discussion of antiderivatives, and we'll take them quite a step further and be able to finally see some of their applications of what these creatures are, why we want to think about integrals and antiderivatives. And next week, we'll see even more how useful they really can be. But for now, we will kind of continue where we left off. So we had the following situation in the last video. We were looking at indefinite integrals, and I also called these like general antiderivatives. So let me just clean that up a bit. Let's make some more room here. Okay, so this we wrote as this integral sign, which was, like I said, was a stylized S. F dx is equal to capital Fx plus C, where capital F prime at x, the derivative of capital F, where the derivative of F capital F prime at x is little f at x, i.e. capital F at x is an antiderivative and of little f. Of little f at x, and the C is an arbitrary constant. Okay, so what the answer? So in other words, like, we don't have a single antiderivative of little f. We have a whole bunch of them, a whole family of them, and they all differ by a constant. So I want to talk about, well, how do you pick out one member of the family? What is the significance of this capital C that you're adding at the end of this formula? We did not address this in the previous video, and this has to do with initial conditions that you want the antiderivative to satisfy. So, so the first thing in this video, to address, that we will address, is the significance of capital C, of plus C. Okay, so the constant, so let me just say that the constant C in the above formula can be uniquely determined by specifying an initial condition. Put this in quotes, it's maybe not always initial, but that capital F at x satisfies. Okay, so we can specify this. So we get a whole family of antiderivatives, right? Remember, we saw that, if we add a constant, we don't change the derivative. So for a given function, little f, we get a whole family of antiderivatives, capital F at x plus C. But we can specify a particular member of the family. In other words, we can uniquely determine the value of the constant C by specifying a condition that this capital F has to satisfy. And usually you think of it as kind of like an initial condition, a condition like something like we'll see in the next several weeks, but like initial position, something like that. It has to do with the starting point of your capital F in some sense, but we'll play with it for a while. Okay, so let's just do some examples. So find a function f at x such that the derivative of f is 8 times x to the 1/3, so 8 times the cubic root of x, and f satisfies we can think of this kind of as an initial condition, but it's just a condition. It's, you know, we don't know what the observation we're making is here. It's very abstract. So it satisfies some kind of condition that f of 1 is 4. Okay. So what are we told? We're told that we want to find a function whose derivative, right, is 8 times the cubic root of x. And it satisfies, and that function satisfies the condition that f at 1 equals 4. So kind of turning this on its head, it's saying find an antiderivative for the function 8x to the 1/3, 8 times x to the 1/3, such that the antiderivative satisfies this initial condition that at value 1, it's equal to 4. So in other words, this is the problem I was talking about earlier in this in the beginning of the video, in a slightly different language. Okay, so it's good to recognize that. So, and put another way, this question is asking us to find an antiderivative of the function 8x to the 1/3 satisfying the condition f at 1 equals 4. Okay, so we know how to find the whole family of antiderivatives. That's just the indefinite integral by reversing the power rule. We talked about that in the last video. So here's how we'll proceed. So first, we find the indefinite integral. The integral 8x to the 1/3 dx, and then use the condition f of 1 equals 4 to specify plus c. Okay, so let's do that. So we have 8x to the 1/3 dx. We can take out the 8, and we from the indefinite integral. We talked about that in the last video. And now we remember we have this formula for reversing the power rule. So to find any derivatives of x to the n. So recall from last video, we had the reverse power rule formula, which was the integral of x to the n dx was x to the n plus 1 over n plus 1 plus a c plus a arbitrary constant c. And this works for any n not equal to -1, right? So if you remember, when you perform the power rule, you drop the power down in front and you subtract in the exponent, you subtract by 1, right? So the antiderivative of x to the n is x to the n plus 1 over n plus 1, because when you differentiate this guy, the n plus 1 will come down in front, it will cancel with this, and you drop the exponent by 1, you get x to the n. So we're going to apply that again with x to the 1/3 up here. So we get 8 x to the 1/3 dx is 8 x to the 1/3 plus 1 over 1/3 plus 1 plus a c. And we can, you don't need the parentheses there because we always modify the c. We can, put this is a times c, we can call c. We'll specify the c in a second. So you get 8x to the 4/3 over 4/3 plus c. And you want, you can kind of do some simplification, right? So this becomes 24 over 4x to the 4/3 plus c. And this is 6x to the 4/3 plus c. Now we were told, so that is our general antiderivative, right? So this is the general antiderivative of the function 8x to the 1/3, which was the f prime at x, right? Now we didn't want the general one. We wanted to, we were looking for an antiderivative of this guy that satisfied f of 1 is equal to 4. So that we have to use that information to specify this plus c, the constant c. Now we want our antiderivative little f at x, in this case, because we're going from f prime to little f, so it's a little bit different than the general case, to satisfy f at, f at 1 equals 4, right? So we use this equation to solve for c. So we want, if we plug in, so f at x is equal to, the general antiderivative is equal to 4/3, 6x to the 4/3 plus c. And now you say f of 1 equals 4. So that's the same thing as saying 6 times 1 plus c has to equal 4, right? And then we can just rearrange this. So we get c equals 4 minus x or equals -2. So the unique function f at x, capital F at x, that we are looking for is 6x to the 4/3 minus 2. So this is the f at x we want. Okay, so that satisfies, the fact that this little f at x gives us that if we plug in 1, we get 4, and the value, its derivative is exactly 8x to the 1/3. So that's what we wanted. Okay, well, this one's this is kind of a bit of an annoying example. You'll see it on the homework. It might seem a little impractical as to why you do something like this. So let us see an example where you can actually see why. An example where you want to find an exact antiderivative using an initial condition, one particular antiderivative that can occur in applications. So here's another example, and this might hit too close to home, but we'll deal with it for now. So a flu epidemic hits a town. So let P of t, like I said, it hits a little too close to home. Let P of t be the number of people in the town sick with the flu at a time t, where t is measured in days. So I'm getting ahead of myself here. Sick with the flu at a time t, where t is measured in days. From the start of the pandemic, the epidemic. Not a pandemic, it's just one town in this case. A little bit better. And we know, suppose that at the initial condition, so when the epidemic started, 100 people had the flu. So they all came off some cruise ship or some other thing, came back home, and they all had the flu. 100 people of them had the flu when the epidemic started. Now, in applications, right, and this is true of the was true of the COVID thing too. What you know is kind of the rate. What you can estimate at least is the rate of the spread, right? So you don't know the formula for like how many people are sick at a time t. What you do have an idea of is the rate of the spread of the virus, and that's usually something you can measure from epidemiological data, how many people you see getting sick at any given time, any given day. So what we have here is the derivative. So let's say, so that in other words, what we know is the derivative, we know the rate of the spread, and we want to conclude something about the total number of people sick in the town t days later. Suppose we know after t days, from the start of the epidemic, that the flu is spreading at a rate of p prime at t equals 120t minus 3t squared people per day. So you know that t days after the epidemic starts, that 120t minus 3t squared people per day are getting sick. And now the question is, find the number of people p of t, right, who are sick with the flu after 2 days. Okay, so this is exactly like the last problem we did, but it's a little bit more practical in that, you know, it's not just some abstract function that you want it to equal 4 at 1. It's, you know, we know the rate of spread. We want to find the actual function of the value of the number of people who are sick after t days, knowing that we start off with 100 people sick, right? So it's exactly, we're going to proceed exactly like in the last example. So we proceed. So here's the answer. We proceed exactly as in the last example. So first find the general antiderivative formula, the indefinite integral, if you like. Right, p prime, right? And this will be basically p of t plus c. So you find the indefinite integral of p prime, and then use the initial condition. Now, this really is an initial condition. P of 0 equals 100 to specify the c, the constant c. Okay, so let's do that. So p of t equals p of t plus c, or just it's going to equal the integral, the indefinite integral of p of t, p prime of t dt So this equals the integral of 120t minus 3t squared dt. And then we can use our properties in a definite integral, the sum and the multiple rule that we talked about in the previous video. We have 120t dt minus 3t squared dt. And we can move out the 120 from the integral t dt. And I already moved out, I kind of cheated, moved out the minus 3 already. So we have minus integral 3t squared dt. And now we reverse the power rule. So you have 120 t squared over 2, go up 1, so 1 plus 1 is 2, minus 3 t cubed over 3 plus c. And so now I should do some simplifications. So you get 60t squared. And let's see, minus 120t cubed plus c. All right, so I'm just basically what I'm doing, just canceling off these 3's, and I'm expanding the 120 inside. 120 divided by 2 is 60. Okay, so now this is p of t plus c, right? It's like p of t plus c, and we can specify the exact, what we want to find exactly, the plus c that we need with the initial condition. So we use the initial condition to find plus c, to find the constant c. So you get p of 0 is 100. So basically this is very easy. So you get 0 equals 60 times 0 squared minus 120 times 0 cubed. Oh, sorry, 100 equals plus c. So 100, this is all equals just to 0 plus c. So c is 100. So the particular antiderivative we're looking for is 60t squared minus 120t cubed plus 100. So the number of people sick after after t days is p of t equals 60t squared minus 120t cubed plus 100. Oops, sorry about that. Okay, so that's the kind of thing that's the significance of the plus c. It's like specifying an initial condition for your antiderivative, or some kind of condition that your antiderivative has to satisfy. It's usually an initial condition. It's not always that way. Oh. I just realized I made a bit of an error. This is a common thing. So sorry, the 120 doesn't multiply everything. The 120 is only multiplying the first integral. So this gets multiplied by 120. Let me fix that. Okay, so that changes things a bit. So we don't have a 120 here. Okay, then that doesn't change the calculation of the c, because you have 0 anyway. Okay. Yeah, one thing about these, when you're kind of dealing with, this is an important point, when you're dealing with like several integrals and you're pulling out constants, be careful that the one in the front, make sure you know which integral it goes with. Like write parentheses kind of carefully, because it's easy to kind of over expand like I did there. So this 120 just goes with this integral here, and then you're good. Okay, so I'm gonna clean this up a bit. All right. So now the next topic. So actually, you know what? This kind of, maybe what I should do is put the next topic, this definite integrals, into a separate video. So let's put that in. Let's just do this as a small exercise, a small video, and then we will have the definite integrals be the next video, so I can kind of do all that at once. Otherwise, this is a more natural place to stop than it is to stop in the middle of the next video. So this is taking a bit longer than I anticipated. So I apologize for that.